Hello, welcome back to Every Problem. This is Stewart Calculus, section 1.4, problem number 30. Problem number 30 says a bacteria culture starts with 500 and doubles every half hour, so they're asking how many bacteria are there after all of these different intervals, right? 3 hours, some abstract t hours, and 40 minutes, and then we're going to graph it at the end. So this will be a slightly longer problem, but nothing too crazy. So after 3 hours, well, let's see. It doubles every half hour, but they're measuring most of these in hours. So here's what we're going to do. We're going to write starting. Do I have like a different shade or something? This is weird. What's this? It's kind of grayish, right? We'll have to figure out how to fix that. Maybe that? There we go. Okay. So, anyways, our starting value is going to be 500. So, and it's going to be 2 times larger every 30 minutes. But if we're measuring these in hours, well, 30 minutes is equal to half an hour. So we could also say every 0.5, 0.5 hours. So pretty much what we end up having here in our f of x equals cb to the t. C, our coefficient, is going to be 500. B is going to be 2. And it will double every, it'll double every 0.5 hours. There's a different equation that I like to use whenever it's growth and decay. You might have seen it before. People call it PERT sometimes, where they'll say P equals P initial times E to the RT, where R is a rate, E is just E, P initial is what you start with, P final is what you end with. But anyways, for part A, it's simple enough where we can just make a chart. We can have it 0. At 0 hours, we have 500. At half hour, we have 1,000. Because this is just doubles every half hour. First hour, we have 2,000. Second, let's see. 1.5 is 4,000. 2 is 8,000. 2.5, 16,000. And lastly, 3 is going to be 32,000. So, how many bacteria after 3 hours? We could say 32,000. Good, okay. How many bacteria after T hours? So here's what I'm going to do. Everyone has their own way of doing this. But like I said, the way that I like more when we're dealing with continuous, it's called continuous growth or continuous decay, right? So this population doesn't just magically double every 30 minutes. It's not that it's at 500 and then immediately at the 30-minute mark, all of it becomes 1,000. It's not like a step function like this. It's more so, one of these curves. So that's where I like to use the PERT equation. So suppose we have this. We have P equals P initial E to the RT. And we want to find the doubling time, which we know is, we want to find R, but we know the doubling time. So it doubles every 30 minutes, right? So we have the final amount, 1,000, equals 500 E to the R times, it doubles every half hour. And we're measuring T in hours. So we'll divide everything by 500. And that gives us 2 is equal to e to the 0.5r. Now we're going to take ln of both sides. Ln of 2 equals ln of e to the 0.5r. Now, one thing with ln properties is you can drag the exponents down to be a coefficient instead. So now we have ln of 2 equals 0.5r ln of e. Ln of e is just 1, so now we have ln of 2 is equal to 0.5r. Divide by 0.5. And now we have r is equal to ln 2 over 0.5, which is the same thing as saying 1/2. When you're dividing by something like that, you can also flip and multiply. So that's the same as multiplying by 2 over 1. That gives us r is equal to 2 ln 2. Okay. Perfect. So now we have our r value. So we have p is equal to 500, that's our p initial, times e to the 2 ln 2 times t. Okay? And there we have it. That is our function for some number t hours. That's how we solve for the population. Okay, so we've got that. That's for part B. Part C, how many are there after 40 minutes? Okay, well, let's use this equation. We'll have P is equal to 500 e to the power of 2 ln 2 times, okay, well, t, we're measuring this in hours, and they're saying 40 minutes. Well, let's see. There's 60 minutes in an hour, so that's 40 over 60, which equals 2/3. So we're just multiplying this by 2/3. Excellent, okay. Now, well, we just have to do the math now, so I've got my calculator. I'll calculate just what's in the exponent first. So I'll do 2 ln 2, hit enter, times 2, divided by 3. Then I will do e to the answer. That way it can be as specific as possible. And then multiply by 500, the coefficient. And we get roughly, we get 1,259.92. So you could round up or down, depending on how they want you to round, but we will just say approximately 1,260. Okay, great. Now, part D, this is the last part. It says, graph the population, estimate the time for the population to reach 100,000. Now, we can actually check to make sure that our function is good by looking at this doubling time chart that we made for part A. With the doubling time chart, if we had 3.5 hours, that would give us 64,000. And 4 hours would give us 128,000. So they want to know some number for 100. I'll use a thinner pencil for this. They want to know some number for 100,000. And so we know it's going to be between 3.5 and 4. So as long as we have that, we know that we have probably written the correct function. So just one moment, if there's any noise, I just have to set up the keyboard. Great, okay, so 500 e to the 2 ln 2 times t. Let's go ahead and do that. So we have y equals 500e to the power of 2 ln 2t. Okay, here we go. This is the moment of truth, right? We're going to get all this going. They're asking about 100,000, right? So here we are. 100,000, you can see on the left side of the screen. And if I tap that point right there, right about, what, here? 3.882. And, well, that's pretty cool because 3.882 is right in between 3 and 4. So we can go ahead and erase that. And we can say it's about 3.882. Sorry for the bad handwriting. I'm writing at a different angle now. And that's going to be it for part D. So I know that was kind of a long problem. I hope the PERT form is useful. I think it's really good whenever we have continuous growth or continuous decay. So yeah, that's everything, and I hope it helps.